Right, Sam? Okay, 4 more lectures, including this one. So there's going to be a little bit of intensity in these last 4 lectures, formation of the last one. We're going to connect a lot of things we've talked about. We still have row reduction. We still have all that stuff, elimination, right? Now we have eigenvalues, we have pivots, we have all these things. We're going to start connecting all these things together and find out more and more about our friend the matrix A. Okay. I'm somewhat functioning now, so this will be good. Okay, so I'm going to talk to you a little bit more about this beautiful factorization of matrices that are symmetric. So if A is A transpose, then we came up with this story that you can diagonalize it. It's a diagonal matrix here, the eigenvalues are on the main diagonal. Eigenvectors are in here as columns, and this is simply Q transpose. So more generally, it's S lambda S minus 1. Inverses are nasty, right? So that's not as pleasant. This is pretty spectacular. The inverse is just the transpose. It's an orthogonal matrix. So we're going to talk a little bit more about that. We have to show, very roughly, we're just going to give you an example of why these matrices, symmetric matrices, always have orthogonal eigenvectors, even when an eigenvalue is repeated, right? So there's this delicate problem we can come across, it happens pretty easily, where eigenvalues are repeated. That's this algebraic multiplicity thing, which is in a lecture online. And we may have a geometric multiplicity that's less than algebraic multiplicity. Not enough eigenvectors. We call it a deficient matrix. Okay, we're going to have a little interlude on traces. I'll show you a charming, everything is charming in Matrixology. I'll show you a charming little result about traces. It has lots of power, actually. And then we're going to do things, we're going to start on a little off to the side piece where we're going to connect pivots and eigenvalues in this deep way. We're going to actually get to something like this and see how this can be better thought of with matrices. So what elimination really does, if we have symmetric matrices, it's all going to be with symmetric matrices. We have this strange connection between eigenvalues and pivots. We already have one, which is that the product of the eigenvalues is equal to the product of the pivots with plus or minus and equals the determinant of A, which is pretty strange. Which ultimately is the volume of the geometric shape framed by the rows of A, or the columns of A. We're going to talk about this new thing, positive definite matrices, which seems like a strange thing, and then we'll have semi-positive definite matrices. And then we'll get eventually to when A equals A transpose is like a real number. You kind of take a square root of it, a real positive number. Positive real number. Bit of a stretch here. So there's lots of little bits and pieces here. And then we get into this big story of SVT, and that's the finish of the course. This is a really fundamental thing that's used over and over and over. Lots of areas, has different names, but singular value decomposition because it was made up by people in the 1800s. It's not true, is that true? Anyway, the words are fun. Singular, as in a singular chat. Sort of that's strange. Okay. You do the whole lecture. I can speak like an Australian. Okay. All right, so there are a couple of things up there. This little tweet has been waiting to come out for several months. We have a practice level for you. Practice challenge level, where is it? So if you go here, oops, challenge levels. If you go here, you will find here, there's a practice level. Important point, next week is an exam on the Tuesday, right? And it involves these 3 levels. Gallagher, Pitfall, and Qbert, the sad Qbert. So, all right, so solutions there as well. So you can work on that. You should practice that. We are up to Qbert. Qbert is due next. So this was Pitfall. Qbert is due next Tuesday. And again, there will be office hours. Well, office hours will be complicated. I'll send out an email as a visiting person. Okay, I'll send an email. There will be office hours on Monday. So this is going to be a little, I'm going to throw away some of the stuff that I don't want to talk about because I realize it's relevant, and I'll just show you beautiful things. All right. Okay. So we got this. Okay. So last time, right? We managed to get to if A equals A transpose, and the entries of A are real. Right? No complex numbers in there. Then we got to this beautiful factorization, Q lambda, Q transpose, and the eigenvalues lambda 1, lambda 2, lambda n are all real. Right. Now we didn't prove completely, I give you illustrative part. Right. Okay, so there was one piece that was floating around. So we recall this nasty, sad story. That diagonalization will fail if you don't have enough eigenvectors. Let's just write that out in words. Diagonalization fails. It was not possible. Right? It's not possible if we don't have, or A, let's put it, if A does not have, this is great, does not have n linearly independent eigenvectors. And the reason is we can't build this story, right? E value. Sorry, I said values. Eigenvectors. Vectors. We'll always have n eigenvectors. And so we can't make S. We can't make an S in S lambda S to the minus 1. We can't build this, and we can't construct that story. And the problem, and we also showed that this can only happen if you have eigenvalues that are repeated as solutions of the characteristic equation. So, this is only a problem, right? This is only possible when E values are repeated, and at least one lambda's algebraic multiplicity. How many times it appears? Algebraic multiplicity is greater than the geometric multiplicity, which is about eigenvectors. It's just there's a way of saying that we don't have enough eigenvectors for that one. Right? So the solution to this thing, A minus lambda times the identity times V equals 0. Let's say this has appears k times in this A minus lambda, the determinant equals 0. Then we need a dimension k eigenspace. Right, a lot of words. So we don't have that, we don't have enough eigenvectors. So because we can only just write this equation down once. If they're all different, lambda 1, lambda 2, lambda 3, they're all different, we write down a separate null space problem for each one. Each one will give us a vector, and we were able to show that they'll all be linearly independent. Okay, so I'll just give you a tiny little example of why this is not a problem for symmetric matrices. Okay? So, kind of why symmetric matrices are awesome. Part 7. We're going to have lots of good things about this today. Awesome. Part 17. Okay? All right. So this is not a problem. So all n by n symmetric matrices have, we're just going to do it, have n linearly independent, orthogonal, that's the big deal, even better, orthogonal eigenvectors. Incredible. Right? They form a really, we really like I hat, J hat, K hat. We can build that structure all the time. So it turns out these matrices produce these things for themselves. All right. Here's just a little example. Right. So let's just take an example, and this is all we're going to do. A equals two examples. 1, 1, 0, 1. We'll work our way through these. A equals 1, 0, 0, 1. All right. Now, people can, I've seen this, it's easy to go wrong with these, with eigenvector and eigenvalue calculations. So let's just think about this one. This one's going to be easy. Right, so step 1 is solve A minus lambda I equals 0, the determinant of that equals 0. So let's do that. So it's 1 minus lambda times 1 minus lambda, and then here's the other part is minus 1 times 0 equals 0. Often this part gets dropped off. It doesn't matter here because we've got zeros. Okay, but yeah, we've got to concentrate on this little piece. Yep, yeah, falls off. All right, so let's see. So this is fine. It's 1 minus lambda squared equals 0. So lambda 1 equals lambda 2 equals 1. So lambda equals 1 has an algebraic multiplicity of 2. And over here, what do we get for this one? The only difference is that 1 sitting there. This, so this is this one, and this one over here. Write it again. Right, it's going to be 1 minus lambda whole squared equals 0. And again, we get lambda 1 equals lambda 2 equals 1. So both cases, lambda equals 1 has algebraic multiplicity of 2. Now, this A is not symmetric. This A is symmetric. Let's look at their eigenvectors. So let's get to the next step. So this is always part 1. Part 2, find E vectors. And, oh, do you want me to do that? Can I just write them down? Do what you feel. I'm just going to run it down because I think you should be able to do it. The eigenvectors for this, you only find this. You get, so for, let's write them like this. A equals 1, 1, 0, 1. We only find, so this is lambda equals 1. It only gives us V1 equals 0, 1. What am I saying? 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Yep, good, 1, 0. Okay, all right. Right, good. So that's good, but no V2. So this is a bad matrix. Yep. Over here, A equals 1, 0, 0, 1, which is of course the identity matrix. If you go through the process, you'll get V1 equals 1, 0, and V2 equals 0, 1. There's a choice here. You can choose 3, 0 and 0, 4. Fine. But these are nice choices. Right? This is a nice basis. Nice basis for eigenspace, for the eigenspace of lambda equals 1. So it seems funny to work with the identity, but the identity, what happens when you multiply a vector by the identity? You just get the vector back, which means it's got an eigenvalue of 1. You didn't change it. And every vector is an eigenvector of the identity. Exciting, you know? Okay, so this is a good matrix. Good matrix. Good matrix. Give it a little bit of kibble. Okay, this one. So let's see, so what is going on? They both have lambda equals 1 twice, but there's something went wrong with this one. So how do we, so this is a symmetric matrix, that's the story. A transpose. That's the thing that guarantees that we'll always have two eigenvectors. Let's see. Just sort of illustrated example as to why that is. So what we're going to do is tweak each one. Tweaking. So one mathematical thing. So do a slightly different with this. So tweak matrices. Okay. And we're going to add a little epsilon in here. So we'll say we'll have A equals 1, 1, 0, 1 plus epsilon. So it's this matrix with a little plus epsilon. Shift it off a little bit. And this one, over here, we'll put our little, we'll do that here. 1, 0, 0, 1 plus epsilon. So epsilon is small. Small and is small, and we're interested in what happens as it goes to 0. So as it goes to 0, it's going to come back to these two. All right. So we go through and we solve everything again for this 1 plus epsilon group. So we find, you go through, you do all these things again, you'll find that lambda 1 equals 1, and now lambda 2 equals 1 plus epsilon. So they're different, and we don't have this problem anymore. They're different. So now, right, so it's now different, now separated. But you can see as epsilon goes to 0, then lambda 1 will approach, or lambda 2 will approach lambda 1. So we'll collapse back. Right? Fair enough. The matrix itself collapses back. Okay, that's true. And we know at this point, because they're different, they'll have different eigenvectors. And you can go through and find them. You'll get 1, 0, which we had already. And now there's another eigenvector that pops out. It's associated with lambda 2. So this is for lambda 1. This is for lambda 2. It has its own eigenvector now. And it is 1 and then epsilon. So if you stare at this for a little bit, the problem is that as epsilon goes to 0, these two eigenvectors are going to become the same thing. Right? It's going to collapse. So the eigenvalues are going to collapse together. They're going to end up being the same. But here the eigenspace is collapsing as well. It'll end up being one-dimensional. Alright, so let's look at the other one. So similarly, you end up with lambda 1 equals, right, 1, and lambda 2 equals 1 plus epsilon. This is all we need to do for this little piece. And we get this, v1 equals 1, 0. But now we get a very different thing. We get v2 equals 0, 1. There's no epsilon in that second eigenvector. This is terrific. No epsilon. Right. So no epsilon. So as epsilon goes to 0, these two approach each other, but these never budge. Right? They don't collapse. And the thing is here, this is a symmetric matrix. This is symmetric with lambda 1 not equal to lambda 2. And we've known from before, so from before we have that this implies the E vectors are orthogonal. And we see that. So let me just draw a little graphical thing here for you. So this one looks like this. It's a 1, 0, and a 1 epsilon. So it looks like there's a 1, 0. So this is V1 is here. 1, 0. And then 1 epsilon looks like this. This is V2 equals 1 epsilon. And so as epsilon goes to 0, these collapse. So as epsilon goes to 0, E vectors collapse onto each other, right? But this picture, this other one, we have V1 out here. It's a good, healthy eigenvector. And V2 is here. V2 is 0, 1. Yes. And these things are at right angles for all epsilon greater than 0. So orthogonal for all epsilon greater than 0. So there's no way as epsilon goes to 0 that these can go jump. They can't jump. They can't collapse. So there's no collapse here. So the idea is, in general, you've got an n by n. You use the result that if all the eigenvalues are different, then we have that they're orthogonal, the eigenvectors. Eigenvalues are different, distinct, then eigenvectors are orthogonal to each other. So we do that, we take any matrix you have, and you add little epsilons here and there, and you spread them out so you can make all the eigenvalues different. And automatically you get this nice big right angled structure. And as those epsilons go to 0, this can't collapse. But this one will. This one will collapse because there's no guarantee it's not a symmetric matrix. Exciting? The great truth is that for every symmetric matrix, you can always write down this factorization, Q lambda Q transpose. And it takes some work to find the eigenvectors, so that's a problem. It does take some work to find eigenvectors and eigenvalues. And often you're dealing with 3x3s and 4x4s. Then it's easy to find the inverse. It's very simple. It's a lot of beautiful structure. Wow. Okay, so that's, I think, all I want to say. Now this is what's on next, right up until now, and then maybe what I talk about with the trace, maybe or maybe not. This little bit about the trace. This will be challenge level 3. Now, the temptation, of course, is to ignore all this, but we'll be on the final exam. So, which, because this is a real course, is cumulative. All right, so. Okay, so I'm going to tell you, as I said, I want to use that word, charming things about traces. That's good. Information loss issues, okay. Back up the blackboard, okay. Okay, so, yes, all right. A charming feature of traces. Let's write like this, of traces. Yeah. So traces. Traces are these strange things where we sum up, it's for square matrices, we sum up the numbers on the leading diagonal. Odd thing to do. But it turns out that that appears a lot in many calculations. So again, the trace of A, just to say it again, it's an n by n matrix, equals the sum of I equals 1 to n. And this is the entries on the leading diagonal. So we have this kind of magic already known, is that the trace of A equals, what does it equal? It's related to something else about matrices.
This is a question. Is that just when you look at it originally, or is that after you get it in like upper or lower?
Oh, right. Yeah. Yeah, so this is the raw matrix. If you start to mess around with it with raw operations, it's no good.
Okay, so just as it.
But I'll show you a connection in a little bit, which I think connects to what you're saying. Okay, so there is something.
Equals the sum of the eigenvectors.
All right, very good. The sum of the eigenvectors. So we kind of proved that. We'll prove it again because I'll show you a funny thing. So this is kind of, there's a lot of spooky weird things in matrices. I mean, you could also say it's disgusting and horrible, but that's beautiful. It's a beautiful thing. So let's little lies here. Okay, so it's the sum of these things. Right, yeah, so you can't do raw operations. So let's do it. So we've got that's a little note we already have. So let's try this. Often there's a formula for products of things, right? The determinant of the product of A and B is the product of the determinants. the transpose of AB is B transpose A transpose. But strange things. It doesn't always work, but we have these things. So what about this one? Okay. So the monks suggest considering. You never see their faces, it's very disturbing. Trace of AB. Play around with that. Now, it could be the trace of A times the trace of B, or maybe you add them together or something, but it's different. This is a different banana story again. Okay. So, consider this. So let's write it out A times B properly. So this is going to be a little funny. So what's the, if you take A times B, it's the sum, right? We're taking the rows of A dot products with the columns of B, right? That's how we multiply matrices together. Yes? So, I've written them as, yeah. So, the trace of AB is going to be the trace of, it's going to be the sum of the, just by the definition of the trace, the I entry 1 to n. These are both n by n. Right, so again, we just sum down the leading diagonal. So this means the I entry of A times B. What is the ith entry? What is the II entry? What is the 3-3 entry of AB? Well, this thing is the dot product of the ith row and with the jth column of A with the jth column of C. Yes, nice. All right, so that's good. So we can do the right kind of notation. Okay, so sum j equals 1 to n, and so it's going to be A. So the ith row is this one, and the jth column is this one. Right, so this nope, I know we're going for AIJ. Yeah. This is the ith column. That's what I'm trying to say. Ith column of B. This is the ith row of A. And we're taking the dot product, so it's this ith row and this ith column. Is that okay? With the definition of matrix multiplication. So we can do something, we can play around with this now, right? There's a nice looking symmetry here. So we can swap the order of these things. So we're going to swap the order. Right, we'll swap the order of these. Let's see what happens. Again, monks nudge us in this direction. Right, so we've swapped. So now it's j equals 1 to n, and I equals 1 to n. We're going to do this. We'll do this sum first, and then this sum, and then we'll swap these two. bji, aij. So now this, well here, what is this? Right, this is the jth row of B, and it's a little puzzle this one, and this is the jth column of A, and you're taking the dot product of those two things. So if you take the jth row of B and the jth row of A, take the dot product, what is that? So this is all, okay, right? The sum is along that part, like this. It's the entry, right, you may have to look at this one. It's the, it's B times A, J. So now, now J is going from 1 to n. JJ. So it's the sum along the diagonal of B times A, which is the trace of B times A. So this is the weird result for traces. The trace of AB is the trace of BA. No other connections. That's it. Pops out in different ways, right? So I guess there's some. No, it's not really the same. This is a different thing. It's a different thing. Right? You know with say inverses that the order changes, and you'll see why this is different. All right. So that is a charming little result, and let's use it for good. A couple of different ways. So what about this one? I know this is the next question. Cool. You said cool. You wrote cool, right? Cool. I expect you wrote that. So what about trace of ABC? So what's that? What can we do with that? What are we allowed to do with that? This actually told us we can flip things. So we know already that if we have a matrix times a matrix, we flip them. So we can do that. That's all we need to know. So it's the trace of, this is, so we can flip these two, C times AB. And we can flip, we can make this a grouping and this a grouping, and we can flip them. B, C, A. So really what this is doing is we're taking the last one and putting it to the front. And then the last one and putting it to the front. And then if we did it one more time, take the last one and put it to the front. We get this, A, B, C. Again. So it's a cycle. We're allowed to cycle around. We're allowed to cycle these matrices around. So we cycle matrices. So that could be used for fun and profit. All right, so you could, so in general, yeah, right? You're allowed to cycle. Okay, so that's a funny result. So here's here's a nice little application, a lovely application. So if A can be diagonalized in the magical land of diagonalization. Always true. If, then, we can say the trace of A equals the trace of S, our lambda, S to the minus 1, like this. So what would be a fun thing to do with this? Raise it. Yeah, so you can cycle, we can think of cycling in lots of ways. We can move this one to the end or one to the front. So we can cycle. So this would equal the trace. Let me sort of put circles around things. So we'll make that a grouping, that a grouping. You can make that a blob and that a blob, and that would be fine. So we'll swap those ones. So it'll be S to the minus 1, S. All right, what happens now? Joyous land. Cycling matrix. Victory, all right, it's victory. General victory. So, identity matrix. So it's the trace of the eigenvalues. And so, this is true, actually, the trace story is true in general, so we haven't proved it for anything because we may have a horrible matrix that can't be diagonalized. But trace of A is equal to the trace of the lambda, the eigenvector matrix, which is just the sum of the eigenvectors. So we didn't prove it quite in general, but it's very nice. It came out very sweetly, very sort of easily. Right? So again, this is lambda 1 down to lambda n 0. That was proved. Except the 97 is the 9. All right, okay. All right, that was great. Okay. So I'm going to skip some things here. And I actually have the movie written down. Okay, all right, so consistency. All right, good. Okay, good. So that's a little thing about traces. It's a fun little thing that could pop up as a little question. Or if you're solving something to do with quantum mechanics or general relativity. Casually, in spare time. Okay, traces. So we're going to move on to the next part. So this is going to be this whole business about positive definite matrices and this connection between pivots and eigenvalues. We're going to tie all that up probably on Thursday, and then we're into the world of SVD. Which kind of sounds bad. Okay. Okay. So, new thing. That was a palette plan. New thing. Going to be positive, definite matrices. Definite matrices. It's called PDMs. And a surprising connection between eigenvalues and pivots. Between E-values and pivots. So we're going to go off in a little, we're going to explore some other territory, sort of like we did with determinants. We went rummaged around the determinant box and then brought back some things that we did. But we explored more than we did too. So, what's a PDM? So a PDM equals a n by n matrix, n by n symmetric matrix. You may wonder why these things are here. I'm not going to tell you for a while. A with which has all eigenvalues. So we know they're going to be real. All lambda greater than 0. They're all real. This says they're real. Symmetric. So n by n, I should put right here. N by n, real, symmetric matrix A, which has all its eigenvalues are greater than 0. Alright, that's a PDM. We will accept this as well. Also good. Also acceptable as a kind of a thing that might be of use in general. Is the semi-positive definite matrix. Semi. So it's a now lambda can be greater than equal to 0. We're going to allow some 0. Semi, all right? And then the ones that have mixed eigenvalues, some positive, some negative. We're not going to. It's a little bit upsetting. So these two have useful things. They appear in different ways. And we'll get to that later. But first, we're just going to figure out something. So the plan is going to be this. The plan is one, how to spot PDMs and semi-positive definite matrices in a while. All right, so we're going to hand you a matrix that says, what is this thing? Take it apart, cover all these good things. 1, 2, and then 2, why we care. This part is obviously going to have a. Okay, I have to work on that too. Okay, but we care at least in as much as we have the final example. All right. Oh, and this will be on the 10th point. That's true. Yep. The unnamed 10th point. It's from 1984. Okay. Okay. Yeah. Where are we going? Okay, good. So I'm going to give you 3 examples. So there's symmetric matrices. So we're going to work on 3 examples, which will have a range of problems. I'm going to skip this. Okay, so I'm just going to state this, that we're interested in matrices that are symmetric, that are real, that have eigenvalues that are greater than 0, or greater than equal to 0. About the eigenvalues. And something it's not in this course, a lot of more numerical stuff, it's hard to find eigenvalues. It's a hard thing to do. Computers get very upset when you ask them to do that. You usually find the biggest one. Power method. Maybe the second biggest one, you can do that. Anyway, small matrices, no problem. So 3 examples. So let's call them A1 equals this character, 2, they look suspiciously the same, -1 and 2. And I'll tell you straight away that this one has lambda 1 equals 3, and lambda 2 equals 1. So this is greater than 0, this is a PDM. And then we use an emoji of some sort. Alright, okay. Okay, I really refuse to do it. Okay, anyway, alright. A2, I'm old people. Okay, so 2 minus 1. Now, Apple updates its software. Like one of the big things is that it's going to do emoji keyboard. There's also some other things, but that's sort of the highlights. That's good. 2 minus 1 minus 1 minus 2. It's good. It's good. Okay, let's see. There's this. Lambda 1. You know, there is emoji dick. Do you know someone did this? I mean, everyone should be arrested, but there is an emoji dick you can buy on Amazon. Using Mechanical Turk, putting sentences. Moby Dick is full of long words, right? Moby Dick, which is a metaphor for suffering itself. What's it? Well, you can buy it, yeah. Okay, we're emojis. All right. So this is really how I like to talk. We have a job to do, people. Everyone. It's horrible. You can't understand it. You can't understand it at all. I mean, call me Ishmael, emoji. What's that? Okay. All right. All right, you can go by that. Lambda 1 equals root 5, lambda 2 equals minus root 5. In this little world of pain that we're in now, that means a bad thing. So, not a PDM. Right? A3. What have we done to it? It's just a minus sign. That's all we changed. It's hard to see, right? Eigenvalues are hidden inside these things. Pivots are hidden inside them. A3. Let's do A3. It's going to be all negatives. -2, -1, minus 2. Okay. And we have here lambda 1, if you go through and figure it out, which is an excellent activity later on. Lambda 2 equals minus 3. I've just ordered them by positivity, I guess. So, also, not a medium. But it has 1 positive, 1 negative. This one has 2 negative, and this one has 2 positive. So there's going to be something about that. So if I got these laid out, kind of, okay, all right. So we're going to work on these 3 examples. And you know, we'd be done, right? We've figured out the eigenvalues, fine. But that's a hard business. That's generally a hard business. So it'd be nice if we could do it in an easier way. So that leads us to this other connection. All right. Lots of other things are going to pop up. This is pretty cool. Okay. Yep. Okay, good. Okay, so, excited about this. I know you are. What do I do with my, okay. All right, we've got these things. Maybe some sneaky tricks, of course. So, in general, this is a horrible truth that I've been protecting you from. In general, this is where the bugs with computers come in. In general, computing lambdas is unpleasant and messy, right? So it would be nice to know. It'd be nice to have a simpler way of detecting PDMness, way of detecting PDMness. Right? Okay. For reasons that we have no idea, because I've told you why they're useful or why they're purely. And yeah, some of it, the main reason for this will be here later on. SVD. All right. Okay. So here's the result. So surprising result. Surprising result. So the number of, so if A equals A transpose, symmetric matrix, then three things. We have, a number of positive, I'm going to write number of positive E-values. This is not just a half diagram, right? Does it still mean number of? Oh my God, really? That's not a number of?
No, yeah. They use that symbol all the time.
Okay, pound sign. The octothorpe. This is an octothorpe. The octothorpe tag. It's a great word, octothorpe. They're very nice words for all these things. Slashes of Hercules and so on. Okay, number of positive E-values. I'm going to write it here for you. Octothorpe. Number of, so I did tweet hashtag octothorpe. Okay, number of positive eigenvalues equals the number of positive pivots. The number of negative E-values. This is creepy, strange. It equals the number of negative pivots. And the number of zero eigenvalues. Big deal, those guys. Eigenvalues also equals the number of zero pivots. That's strange, right? We already had it. So earlier, in an earlier episode, we found out that the determinant of A, and I said it out loud, I guess, is the product of the pivots, or the product of, let's do eigenvalues first, and it equals plus or minus, that depends on row swaps, of the pivots, which are D's, because that spells difference. Okay. Right? Strange. Okay, strange. So this is a more detailed thing. It's a weird connection. They're not the same values, but they do have the same structure, the same kind of texture. And pivots are much easier to compute. Yep.
After the octothorpe, is it positive real E-values?
Yes, so because it is so we're drawing all this goodness. A is symmetric, A is real, it means it has real eigenvalues. So that's just true. Yeah. And it means it has also orthogonal eigenvectors. So lots of goodness here. So they're real, and then the question is, are they positive or negative or zero? There's an extra detail, which is not here, is whether they're greater or less than 1 in magnitude. Because if you have A to the n, right, it's the ones that are greater than 1 in magnitude, those eigenvalues grow. They're the ones that grow. Like we did with Fibonacci, you see. One eigenvalue was bigger than 1 and it grew, the other one was magnitude was less than 1 and it okay. Is that okay? Yep. Okay, so we knew this, now we're getting this extra texture, and it means that we would only, if we want to find a PDM, for which we have no reason why we're doing it yet, but if we did, we just have to find the pivots. Easy to do, row reduction. Which you can do while you're eating your breakfast. Okay. This is very strange. This is weird. Super weird. And I'll give you kind of a nice thing that kind of are we okay? I should ask those questions. Okay, this is attached to the wall. Okay. I wonder if they'll let me keep the boards. Do you think they would just eat the whole building? Are they just going to smash those down? They're going to smash them down. Yes.
Do they use the number sign in Australia?
I think Europe, probably.
What do you think? I think they don't in the UK.
Oh, yeah, I don't know. Well, there's also this. There's also this one. Yeah, so we'd have to look this up. Is that one?
All right.
Right? And then 1s are like this, and the 7s are like this, and the z's are like this. These are the few things we can take from Europe. Everything else. But it's good to have 2's and z's, or z's, separate. Right? Z is terrible, it doesn't rhyme. I mean, it's just never going to last. Okay. I watched this mystery. Let's see. Okay, here's a beautiful reason. So this is really strange. So let's do it. A beautiful reason. I'm sure you'll find it beautiful. We're getting to the world with lots of beautiful things. Okay. So let's take that second one, which is buried. I can't show you unless I look this up. Yeah, so we've got these to play around with. We're going to take this one. And I guess I should compute the, we'll get there, I'll compute some. You know what, let's do that first. Okay, let's go back to our examples. So we had A1 equals, yes, I should do this, 2, minus 1, 2. You can educate me about this. Actually, a really weird difference is whether you put a period after Mr. or Ms. That's changes, that's really strange. I don't know, someone's trying to save ink. That took me years to notice. Driving on the side of the road, you figure that out pretty quickly. Okay, all right. Because of death. Okay. So, death is a great one. Okay, so let's see. So we have this. We have lambda 1 equals 3, lambda 2 equals 1. So do row reduction on this. I guess we can do it. Fine. Let's do it. 2 minus 1, so I'm going to subtract. I'm going to add a half of this row to this one. Tell me when I'm getting this wrong. Half of this one. So it's going to be 3 halves. So pivot 1 equals 2. Pivot 2 equals 3 halves. So let's go through them all and see that this is just checking. Right? This is not a proof of anything. 2 minus 1 minus 1 and that's minus 2. And we had lambda 1 equals root 5, lambda 2 equals minus root 5. Scribble these ones down. See if we can make it into figuring these things out. Minus 1 minus 2. Lambda 1 equals minus 1. Lambda 2 equals minus 3. Row reduction would give us 2 minus 1. Now we're going to add a half of that again, add a half of that again, so it's minus 5 halves. Minus 5 halves. D1 equals 2. D2 equals minus 5 halves. So these match. So the signs are matching. Minus minus, plus plus. Plus plus, plus plus. So this is just a little test of examples. And then we would do this business here where we're going to subtract. Right, yep. So the tilde here would give us minus 2 minus 1. We're subtracting a half of this row. Good. So this is going to be minus, it's going to be 0. Sorry, that's a 0. Otherwise, that's a 0. So that's the whole point of row reduction. And we've got that one, and then we're going to subtract this off, so it'll be minus 3 halves. And so we get D1 equals minus 2, D2 equals minus 3 halves. And so that's our matching in. Minus, 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 minus. Okay, so the signs of the eigenvalues match up with the signs of the pivots. They'll be, right, again, it's the number, it's the number. Right, okay. So that's strange. That's strange. So here, let me sort of see if I can get out an example. We won't be able to get all of this down, but we'll get it somewhere. Okay, put this down. This one up. Okay, so beautiful reason actually is here. This is just a little check. First, we're going to check it first. We checked it. Okay. So let's do this properly for A2. So A2 equals 2 minus 1 minus 1 and minus 2. And I've told you we didn't calculate it. We've got this. And if you go through the proper business of row reduction, we'll get this. A2 equals 1, 0, minus a half, 1. Right, our multiplier here was indeed, let's write it out. Let's write out the row operation for just this one. It's rho 2 prime equals rho 2 minus something like rho 1. And the thing in the middle is minus 1 divided by 2. Minus 1 divided by 2. And that little beast is L21. All the way back to stuff we did to start. And so here's L21. This whole thing is L. And over on this side, we have the pivots. We have this thing, 2, minus 1, 0, minus 5 halves. And this is U. Right, so we're invoking early magic that we have, right? So that A can always be written as, with some row operation thing, as a product of these two triangular matrices. Lower, upper, always with ones here. Right? It's the structure of L. Okay, so that connects. So there's something special because these are all symmetric matrices, right? Of course, they're all symmetric matrices. So because A2 equals A2 transpose, we can go one step further than just LU. I think we talked about it just a little bit. What's the next thing we can always do with that? Right. And it becomes LD, very simple. Okay, so there was always LDU. There was always LDU. But if it's symmetric, what's the U? Yeah. Good. So, we can always do this. So let's pull it. We'll just do the example and then we'll have the general formula. I'm going to pull out the pivots here. So there's going to be 2, 0, 0, minus 5 halves. And so that's dividing, we divide this top row by 2, so we'll have 1 minus a half. Divide this row by minus a half, 5 halves. It does feel magical, right? Look at this. This is L, D, L transpose. It will always happen, right? Once you extrude, right? We extrude. I'm just using that word correctly. Extrude D out of U. I'm going to pull pivots out, make them clear, right? So this is in the same. This looks like a Q lambda Q transpose or a S lambda S to the minus 1, but really Q lambda Q transpose. Really quite nice, very nice. Okay. And you see the sort of the guts of the thing is in here. Okay. So we're going to see something special about how the L's work. They actually do something. So you remember with, and I'll say it again, the Q, lambda Q transpose, the Q's are doing a basis transformation. They're not changing X. When you A times X, the Q's just change the way you talk about X. And lambda does all the work. So that's going to happen a bit here too. All right. Let's get this to work. Okay, so we've got that. So at this point we have, so again, we're going to have to repeat this a little bit, but again, A2 has lambda 1 equals root 5, lambda 2 equals minus root 5, and that matches up with our pivots, and D1 equals 2, and D2 equals minus 5 halves. So let's mess with this piece in various ways. So the idea is to smoothly, so again, this is months, insert months. This is a clever little thing to do. So we're going to smoothly change the half, or the minus a half in the L and the L transpose to 0. So we're going to take A2 and we're going to change it into a different matrix. And if we change this into 0, this will just be the identity, and the identity, right? And so A2 will collapse into this. So let's call it, let's make it a new matrix. We'll call it, I'm going to call it got millions of these. Okay, so let's define this one, B of x. So it's just some new matrix, got a little parameter x in it. B of x. So it looks a lot like this character, but it's going to be 1, 0, x, 1. Yeah. And then 2, 0, 0 minus 5 halves. And there'll be 1, x, 0, 1. So we have A2 equals B of minus a half. Right, so when you put x is minus a half in, you get this back. So now we're going to dial it from x, right? So we're going to send x from minus a half to 0, smoothly. Right, just dial it. I'm just going to tune it. And we'll get to B of 0, which is some new matrix here. It's 1, 0, 0, 1, which is the plan here is that this is the identity matrix. And then we have 2, 0, 0 minus 5 halves, and then again the identity matrix. So the identity matrices can disappear. This will just be absorbed, and we have 2, 0, 0 minus 5 halves. So it's a diagonal matrix. It's really the original pivot matrix, just the pivot matrix. So what are the pivots of this matrix? Of this new one? The pivots here were 2 and minus 5 halves. The pivots of this matrix, the same. What are the eigenvalues of this matrix? Yes, because diagonal, when you have diagonal matrices, the eigenvalues are just sitting. So a diagonal matrix, the pivots are sitting there, and the eigenvalues are the same. Okay, so diagonal matrix sneakiness. This is sneakiness. Diagonal matrix means that we have lambda 1 equals 2, lambda 2 equals minus 5 halves, and that equals first pivot, and it equals the second pivot. So we've moved from one matrix to another. And here's the story. All along, as we've gone from here to here, the pivots did not change. The pivots did not change. So what's the determinant of the matrix? What's the determinant of this matrix? It has pivots 2 and minus 5 halves. Minus 5, right? Okay, so I'm going to have to start on a new board. Let's do that. So as we go from here to here, the pivots don't change, the determinant doesn't change. But the eigenvalues do, right? So we're slowly moving the eigenvalues from root 5 and minus root 5. They are gliding over to 2 and minus 5 halves. And there's something they do not do in that time. So think about that. Think about what they cannot do as they change. Lambda 1 is going from root 5 to 2. And lambda 2 is going from minus root 5 to minus 5 halves. So it's a puzzle. Is there anything that they cannot do? Change sign. Very good. They cannot change sign. What would happen if they changed sign? Right. You would hit 0 and then be silent. Okay. We'll leave this here. Okay. Good. This is good. Okay, cool. Aha. So let's run it up here. So we have. Okay. So we have B. All right. So A2 equals B minus 5 minus a half. We tune it to B0. And this is x equals minus a half, x equals 0. And so from here we have pivot 1 equals 2, pivot 2 equals minus 5 halves. These things do not change. No change. Right? They never change as we go along because it's always an LDL matrix. We're changing the L's, that's fine, but the pivots are still the same. No change. So that's D1 equals 2, and D2 equals minus 5 halves. The determinant of A equals minus 5. No change. So that has to be, again, determinant of A, determinant of, let's write it as determinant of B minus 1/2, the determinant of B of 0. That equals minus 5. No change. So therefore, and let's write down the last one. So lambda 1 equals root 5. Lambda 2 equals minus root 5. That one has to become lambda 1 equals 2. And this one has to become lambda 2 equals minus 5 halves. So lambdas cannot change sign. Right? Otherwise, the determinant would go to 0. Just as a simple thing. Right? So otherwise, the determinant of B of x would equal 0 somewhere in minus 1/2 smaller than x smaller than 0. But it never changes. It's always minus 5 halves. It never changes. So this cannot happen. So it has to be that root 5 can't become minus 5 halves. Root 5 has to become the 2. That lambda 1 has to become that lambda. And this one has to become this one. So, because on this side, right, this side, pivots equal the lambdas, B equals lambdas on this side. The pivots do not equal the lambdas on this side, but we know back here that their signs must be the same. So we start on this side, the pivots and the eigenvalues are the same. Draw back over here, they separate, they change. Pivots do not change, eigenvalues change, but they must preserve this, they must have the same sign as the pivots. Is that victory?
What does it say after minus?
Oh, yeah. What's that?
After minus
Minus somewhere in minus 1/2 smaller than x smaller than 0. Is it? No. Yeah. So x starts off at minus 1/2, and x goes to 0. We're going to dial. We're just going to dial it.
I just understand the notation about it.
Okay. Oh, I guess it's. Alright, it's. Okay, I'm going to wave my hand. So that's pretty cool. So, therefore, the signs of the lambdas match signs of the pivots. And we're not going to do it here, but for lambda equals 0s, and pivot equals 0, this sort of thing, can tweak this proof. Right? So you can adjust the proof a little bit. You can move them off 0 and do something. All right, so that's kind of a cool thing. Let me see if this is the place to sit. Okay, so I'll tell you why we're going to do this, why we've been doing this on Thursday, because let's keep it as a mystery. But we got to here, no, we didn't get to here, we got to something. All right? So more about positive definite matrices on Thursday, exam on Tuesday.
Thank you.